Alright, so in this video we're going to look at 10.3, which is two-way tables. This is a way to look at conditional probability of independent and dependent events in a different way that allows us to avoid using those formulas we had from before. So just to remember, independent events are when the occurrence of one event doesn't affect the occurrence of the other. Right? One event doesn't affect the occurrence of the other, whereas dependent events are when it does affect the other. And we had some formulas for this. Basically, for two events happening, the probability is the probability of A times the probability of B. And in dependent, it's the probability of A times the probability of B, given that we know A happened, which is that bar in A. That's because the probability of B changes based on if A happened or not. And so here we have a different way to use that probability without having to use that formula anymore. And hopefully this also makes it clear why those things change. So here we have a table, and this is called a two-way table, right? Because it has two directions to it, right? You have rows and you have columns with different things on it. And this is the results of a survey that the district has given parents, students, and teachers about eliminating auto shop at Homestead. So if someone said yes, that means they want to eliminate auto shop. And if someone says no, that means they don't want to eliminate auto shop. And so what this tells us is the percentages of people who were parents who said yes, parents who said no, students who said yes, students who said no, teachers who said yes, and teachers who said no. What we can also do with this is get some more generalized data. So if I want to know how many people of everyone were parents, well, I can add up the parents who said yes and the parents who said no, and I get 0.64. That means 64% of people were parents. I could add up all the students, so I know 23% of people were students. And I could add up the teachers, and I know 13% of people were teachers. I can go the other way and find the percentage of people who said yes and who said no. So for yes, I can add across that row, and I get about 76% of people said yes. And I can add across this row for 24% of people said no. So I get those totals as well. So now I want to find these conditional probabilities. If I know that one thing happens, what is the probability that something else happens? For example, in this one, I am going to select a parent, and I want to know if that parent wanted to eliminate the class or not eliminate the class. So my event A here is picking a parent, and my event B is eliminating the class, so voting yes. Now, I already know that it's a parent, so I know that A has happened. So I really just want to know, what is the probability of B given that A happened? I already have picked a parent, so what is the probability that that parent voted yes? And so if I look at parents who voted yes, that's 58%. But that's 58% of all the people that were surveyed, including the students and teachers. Right now, we don't care about the students and teachers. We're just looking at parents because we've picked a parent. Of the parents, there are only 64% of the people were parents. So my total here is actually 58% out of 64%. So I divide that. And so when I divide this, I get 0.58 divided by 0.64. That's actually a 91% chance. Right? And that should make sense because we have a smaller group of people to pick from because we've picked a parent, which means we've ignored the students and we've ignored the teachers. The only people left are these parents, so that's 64%. And then off that 64%, 58% of people said they wanted to eliminate it. So that's a huge difference, right? And that's a 91% chance. Let's do one more example with this. So now we'll look at, we're selecting a student. We want to know if that student voted no. So event A is picking a student. Event B is that student voting no. So we're looking at the probability that someone votes no, given that we know that they are a student, right? We've picked a student. So students who voted no, that's 15%. And the total students, that's 23%. And so 15% out of 23%, that's a 65% chance. So if we know that we picked a student, there's a 65% chance that that student voted no. This is where we can see, right? Like if I just had a person who voted who was a parent, is a 64% chance that I picked a parent. But, if I wanted the percentage of people who voted yes, the probability that I picked someone who voted yes, it's a 76% chance I pick someone who voted yes. But if I pick a parent, that probability changes to 91%. This shows that these events are dependent on each other because picking a parent who votes yes is a higher chance than just picking anyone who voted yes. Same thing with a student, right? Probability of someone voting no is 24%. But if I know I'm picking a student, that probably goes up to 65%. So again, those are dependent, right? If I pick a parent, if I pick a student, the probability that someone voted yes or no changes based on that. So now let's look at the teacher scenario. Now we want to know, is this independent or dependent? For students and parents, it seems like it's dependent. So now we'll test for teachers, right? So we want to know, what is the probability of teacher and voting yes? Right, so yes, given that you're a teacher. Well, so yes in teacher, that's 0.1. And how many teachers were there? That was 13%. Right, so 0.1 divided by 0.13, right? There's a 77-ish% chance. And if I just wanted to pick people who voted yes, that's a 76% chance. This one didn't really go up. It basically stayed the same. So these are independent events. Being a teacher does not change the odds of saying yes or not. Whereas being a student or being a parent did change the probability of picking yes or no. And so that's how you can kind of see if events are independent or dependent based on those probabilities. And this calculation hopefully is a little easier and more straightforward than using the other calculations we did in the last video. So hopefully the two-way tables help you make those decisions and find these probabilities in an easier way and a more understandable way where you just have these numbers to add up and divide rather than having to do too much more stuff. Next example we'll look at is with some luggage, and we're trying to see what our best situation is. So we have a flight, they're tracking how much luggage they lose per passenger on 3 different flights. So on flight 1, 10 people lost their luggage, 3 people did not. On flight 2, 9 people lost their luggage, 5 people did not. Flight 3, 12 people lost their luggage, 1 person did not. So in total, 13 people took flight 1, 14 people took flight 2, and 13 people took flight 3. And the other way, 9 people didn't lose their luggage, 31 people lost their luggage. It's not a very good data set. So now let's look at, based on each flight, what is the probability that you lost your luggage? So if you took flight 1, there were 13 people on that flight, 10 people lost their luggage, right? So 10 out of 13. That's a pretty bad percentage. 10 out of 13, that's a 76% chance, 77% chance. If you took flight 2, well, now you had a 9 out of 14 chance. So 9 out of 14, that's 0.64. And taking flight 3, you have 12 out of 13 people, 0.92. So now looking at this scenario, well, it looks like, and in general, right, regardless of which flight, losing luggage, 31 people lost luggage out of 40 overall, which is a 0.78. So looking at the general average lost luggage case and then looking at these flights, it looks like this is my best option, right? That's the lowest chance that I have to lose my luggage. Still not a great chance because I'm still losing my luggage quite frequently, right? 64% chance of me losing my luggage, that's more than half more than 50% chance that I'd lose it. It's not really good. But this is a way to pick these situations, especially when these totals vary, because sometimes looking at just the number of people who lost luggage isn't enough, right? If 12 people lost their luggage, but there were like 100 people on this flight versus 10 people losing their luggage out of 13 people, that's a huge difference. 10 out of 13 people losing their luggage is way worse than even 12 out of 100 people losing their flight, right? Even though there are more people who lost their luggage, there's still a lot more people who didn't lose their luggage as well. And that's what this conditional probability helps us keep in mind. And these tables especially help us see is those differences between, like the bad scenario is possible and might be more in number, but overall it might be a lesser chance. So hopefully this helps with thinking about those conditional probabilities and using tables and gives you an easier, more simple way to calculate those.